we'll be explaining this project. Thank you. This is a wireless ammeter. How it is, a wireless ammeter. In electronics. Okay, let's start this way. Amperage is the unit for current. So we will not be out of place if we say it's a current meter. We also will not be out of place to say it's an ammeter. But this time, this is not a DC ammeter, it's an AC ammeter. Even though the current sensor in it, the job by even though the current sensor in it can actually measure both DC current and AC current, but we have actually decided to actually make this system an AC current or an AC ammeter. So what we'll simply be doing is we'll be explaining the theoretical aspect of it. While it might look practical, while it's practical nonetheless, we'll try and see how we can actually discuss the practical aspect of this project theoretically. What it will do for you, the rest of you, seated, is to give you an overview, an idea of what you would actually be coming in contact with in this course. Shall you understand?
Yes, sir.
Okay. Now, like usual, like I've already been teaching you guys, when a project is given to me, or when I get a project to work on, the first thing I want to do is to actually have a block diagram. The first thing I will do. Many times it actually helps because block diagram will actually take into cognizance the functions to expect a project. So he will be the one that will be telling us the functions or the things he expected the project to have. The project is done already, so it's not like maybe we can actually make any manipulation to anything. But of course, it's actually going to help enrich the discussion. Okay, so it's supposed to be a wireless AC current meter. So my block diagram should use those. I know I'm supposed to have a power supply. How that power supply should be, I don't know yet. I know that I'm supposed to have a microcontroller. How that is also going to be, or what type of microcontroller I will have, I don't know yet. Now, I know that this system is not supposed to have any screen on it. It means if it's wireless, its result is to be sent wirelessly to an Android application or to an Android phone. That's the idea. It's supposed to be an Android based, how do we call it now? An Android based wireless AC ammeter. You can also say that. So if it's going to be wireless, truth is, okay, still in the light of the block diagram, we need, it should be here. We are going to need a wireless transmitter. Are you with me? While on this end, we are going to have our current sensor. So our current sensor feeds the microcontroller. The microcontroller feeds the wireless transmitter. Power feeds the transmitter to the microcontroller, and power feeds the current sensor. So this is what the block diagram should look like.
This is different from what you said.
This is the block diagram.
It's different from what you said.
Is it different? Okay.
That was straight.
That was what?
Straight down to current sensor to wireless.
Okay. We'll see it. The idea here is you can actually come about a design in any way. Okay, can I continue?
Yeah.
Okay. So the first is this: if this system is supposed to be an AC current ammeter, it means that my power supply should be such that includes or that has both AC and DC in it. Are you with me? So follow for my power supply should be able to actually accommodate AC and DC voltage. How we will come about that, I don't know yet. But I know that my power supply should have AC because the word AC current sensing is actually in the phrase. Can I continue?
Yes.
Now, let me quickly say something on the wireless transmitter. Now, there are various wireless means you can actually choose to actually transmit something or whatever signal, whatever value or data you want to send to an Android phone. A very good example is we could have had if the result is to be sent to an Android phone. The question is, what wireless receivers does an Android phone have? An Android phone will mostly have a Bluetooth device to receive or send. Will have a Wi-Fi to also transmit or receive and also connect to the internet. So that has already narrowed down what my wireless transmitter should be. If it was not for an Android phone, we could have actually brought in a ZigBee module. We could have brought in a radio frequency module, the one I said operate at 433 megahertz. We could have actually brought in an infrared transmitter, and then we have a receiver on the other hand that has what? The TSOP XS series that we had also discussed in this class. Abi? So, what other wireless module do you have used? Tell me. What other one? You don't know yet. No one, you guys will know. So, but since it's an Android phone, we want to actually put in a transmitter here that will know its receiver will be available on an Android phone. Are you get me? So, and if you pick up an Android phone, you know you're either going to have a Bluetooth or your Wi-Fi module. So, our wireless transmitter here is going to be what? Bluetooth. And if it's Bluetooth, we are going to be using the AC05. How did I know? I googled it. I went online and searched for what? Wireless transmitters. The current sensor that was used here is the ACS 712. Again, there are various types of it in the market. Where's my phone? Let me get my phone so I could also check some things. Why? Now, if you go online, sorry. If you check for the ACS 712, let me just so you do not look as if I'm saying everything from my head. I'm not. I'm saying them based on what was online. ACS 712 current sensor. Okay. Now there are various types of it. I think they actually the different types is based on what amount of current they will be able to actually measure. Do you need all of these details, or should I just go ahead? Or
no, I've checked all these.
You checked all these details before, Abi? Okay, thank you. So I'm not sure which one we use. I think we use the one of the 20 amps, Abi? One of the 20 amps was what we use.
Yeah,
We got the one of the 20 amps. So if we say we got the one of the 20 amps, the implication is that this current sensor will not be able to actually measure above what? 20 amps. Sure, you understand? Okay? Then the next thing will also be that we need a microcontroller. But to determine what our microcontroller will need, we'll first of all first of all ask, how does the current sensor send out information? How do we it communicate? The current sensor communicates using what? ADC, analog to digital converter. So which means whatever microcontroller we will use will be the one that uses what? Or that has the feature to do what? Analog to digital conversion. In our previous class, we were mentioning there was this part number we had on the screen before I claimed the board. Was this PIC 1654A?
Yeah.
1654A does not have ADC, so we couldn't have used 1654A to actually achieve this design. If you wanted to use 1654A, so just take this for the record. If you wanted to use a microcontroller that does not have analog to digital converter internally, what we will use is that we will go to the market. We are going to buy an ADC IC. There are chips that are dedicated for analog to digital conversion. So we are going to have something like this. You are going to have your sensor, connected to the ADC converter. The ADC converter is now going to have outputs. Some of them we have 4 outputs. Are you with me? That's some of them for 4-bit communication. Are you with me? Then it is that output that will now be connected to your what? To your microcontroller. So that while your sensor senses information to the analog to digital converter, it converts and sends digital or binary representation of whatever it has read based on whatever settings you have set, like your positive voltage reference or negative voltage reference and the rest. That's what it then sends to the microcontroller. So what the microcontroller will be reading will be values. And if it is 4 bits, it means the microcontroller will be able to read values from between 0 to if it's 4 bits, 1, 2, 3, 4.
Okay,
It's going to
0
be.
to 3.
Are you with me? Which should be 2 raised to the power 3 plus 2 raised to the power 2 plus 2 to the power 1 plus 2 to the power what? 0. This will give you what? 1 plus 2. Tell me, plus what?
4.
Plus what?
8.
So 8 plus 4 is what? 12 plus 3.
14. 15.
So you'll be able to read from between 0 to what? 15. Are you following me? If it was 8 bits, it means you'll be able to read between 0 to what? 255.
Yeah.
Sure you get. Now that is for 8 bits. If your ADC was a 10-bit ADC, it means you'll be able to read from 0 to 1024. That will be 10. That will be 2 raised to power of what? Of 10. Are you following me? That's going to be what? 1024. Does it make sense?
Yes, sir.
I'm just saying that that should be what digital representation you are going to get based on what the sensor sends to the digital to analog converter. But this will require that you bring in another component or another IC. Sure, you are getting my point now. Now, but since we know we can actually get a microcontroller that already has that as an internal feature of it, there will be no point bringing in an ADC IC. Sure, you understand? Okay. So that is why our circuit diagram would not look this. Okay, I just thought I'd say that. So we are going to use a microcontroller that has ADC. The closest that I would have used, of course, which is what you have on your board, is a 20-pin microcontroller. Will be the PIC 16F8760. It has ADC. It has the feature to actually carry out ADC functions. Okay. Okay, so let me look back at it. Okay, so that is it. Okay, can we continue? Now, another thing that I just saw on the circuit diagram that I did not also discuss that if we are designing a system, if you are designing a system, one other thing that I actually do in some of my systems is to actually make it foolproof. Foolproof in the sense that if we have said that this system is meant to read 20 amps, there ought to be a way where we can create some level of protection for the system. In the event that a client comes or a user comes and wants to use it to read more than 10 amps, more than 20 amps, when that happens, we expect that instead of that load damaging the current sensor, and we require that you now, begin reconstructing the system again, or you now go to the market to begin to buy a current sensor. Why that could happen? What we could also do is to limit a user. Are you with me? So that we limit you to maybe say half of this. Are you following what I'm saying now? If I needed to read 20 amps at maximum, I wouldn't have gone to the market to go and buy a 30 amps current sensor. I will have bought maybe a 30 amps or a 40 amps. I will now bring in a relay or another device. I've mentioned it already, a relay, that while this system is monitoring the current drawn, as long as current drawn is still within what I've set it to be, it will, allow the relay to keep impressing voltage on the output. The moment you begin to draw outside what I've actually set it, to measure, it will just triple. Are you with me? And don't forget, we had already discussed that when there is no load, of course, there will not be what? Current flow. Alright, so there's something I've not put in. That is to mean that our system goes into a relay. Are you with me? Then the relay now goes into our load. Does it make sense? So, but what we have done in the case of this project is that we have limited to what? 10 amps. And to limit it to 10 amps, it means we have also gone to the market to go and get a 10 amps relay. But of course, we have a 10 volt DC relay at what? At 10 amps. All of this we are actually going to discuss in the course of this. So I saw that picture and I thought I should mention it. And that's that we have on this board is that we also have an indicator. We didn't put that there. We have a LED indicator. Of course, the essence of that indicator, cannot be overemphasized. You should know we should have an indicator. If we don't have a screen, an LCD screen on board, the LCD screen, if it was on board and was on, we will see that it was going to have light, so we know the system is on. Now, if it does not have an LCD on, and say my phone is in my pocket, from where I'm supposed to actually get response from, there should also be an indicator that tells that the system is on. That's why we have an LED indicator. Okay, that's an LED indicator. Can I continue?
Yes.
So, having understood what the block diagram is, the next thing is how do we now bring in all the different parts that form the circuit diagram. Now, we have already established that we are using a 20 amps AC AC 712 20 amps AC current sensor. Now, we will not when you are actually supposed to draw a circuit diagram. First of all, for you to actually tell what voltage requirements you need on your board, you need to know what the voltage requirement of everything you want to use on that board will be. Now, if you pick on the current sensor, I'm not going to also say all of this from my head. Let me just get out some very good details. It will help this class. You realize that this AC. I'm coming. Please don't mind. It's important. I need to get the data sheets to be able to actually explain. If you look at the ACS current sensor, the current sensor has two parts. It has a part where you feed in your AC. Are you with me? So this is where your load takes AC, like having your life on neutral. It has another part, which is the DC part. At that DC part, you have 3 wires there. 3 pins there. You have your ground, you have your house, and then you have your VCC. Are you following me? Now, on this, what actually does happen is that it has an oil effect sensor. What an oil effect sensor is? We'll discuss that later. This is all you should just know basically, so that you can actually maybe through this class. Is this that when you put in AC and current is being drawn here, what happens is that there is a digital output. Are you with me? Yeah. In volts that represents the amount of current that is flowing here. Let me draw this in some practical way. Let me draw this somewhere. Please look up. Assume you have a source. Let me put it here. A voltage source. It means you have life, then you have neutral. Can I continue? Mm-hmm. And then you have, and say maybe you have an AC bulb. Your bulb has life, your bulb has neutral. If I connect, please look at it. If I connect the life of my source to the life of this bulb, and I connect the neutral of this source, are you with me? To the neutral of this bulb is going to come on. Mm-hmm. And when this bulb comes on, current will flow. Okay, so watch what I just want. This is very, very important. If I connect this life, just watch it and I put it in, I take the neutral and I take it. This bulb will come on. If I need to measure current, I just show you how you measure current. If I need to measure current, what I will do is to cut one of the sides and place my ammeter here. I'm going to read current because don't forget, current will flow. Are you with me? That's how you read current. You read current through. Well, if it was voltage you wanted to read, you're going to read voltage across. Are you with me? Yeah. You read voltage across. But if it was current, you read current on one of the lines. Whether it is on the life or the neutral side, you can actually read your current. Now, if I don't want to use this line, I can remove my ammeter from here, close this line, and then do what? Open this place, and then place my ammeter here. And I'm still going to measure current. Are you following me? Now, if that's what I want to do, and this man is supposed to be my current sensor, or more like my ammeter, what it means is that I'm not going to allow this wire to come this way now. Are you following me? What I will do is that from my source, look up, I could just take the neutral here to the live here, this one here, and then what happens? The one here does what? Go here. Did you see it? What I've still done is just bringing the AC side of the current sensor to measure current flow. Are you with me? So as this bulb comes on, current flow is read by this man on this side, by the current sensor on the AC side. What it will now do is that it's now going to give an impression, a DC value on its output. Of course, that is after you have given it VSS and you have given here what? Your positive 5 volts. Which is your what? Your VDD. You can then source this output into an ADC to keep measuring what amount of current that is flowing on its high voltage current side. Sure, it makes sense. Forgive me, I'm actually just trying to run through it. So forgive me. Do you get the gist? Yeah. So this output is what you impress into the ADC input of your microcontroller to read. So if you look at it, this system actually helped you create this kind of isolation, such that irrespective of what happens on this side, whether there's a bridge or this place blows up, it does not affect this side. And irrespective of what happens on the current sensing side, on the DC side, it also does not affect what is there. Does it make sense? Yes, sir. Does it make sense? So that's basically how the current sensor works. But from the illustration I just made now, or I just spoke on now, you realize that the current sensor will require both AC side, AC voltages, and what? DC voltages. The AC voltage it is going to require is going to be what? The one in the range of what? 220 to 240 volt AC. That's NEPA voltage or generator voltage. Why on the DC side it's going to require what? 5 volt DC. So if I'm to design a circuit diagram and I want to talk on my power supply, I need to know that my power supply should be able to be such that I can provide what? 220 volt AC and what? 5 volt DC. Does it make sense? Yes. So that's the first thing about the current sensor. I just need to say that quickly. Of course, there's more to say about it, but let's just leave it at that. Can I continue? Yes. Okay. So notice something that we are going to need what? 220 volt AC and what? 5 volt DC. If you are going to make use of what? This current sensor. If you are going to make use of this microcontroller, the microcontroller operates with 5 volts. I'm not going to look for a data sheet to tell you that one. So this somebody else needing what? 5 volt DC. Check out, continue. Your Bluetooth module, the AC05, also requires what? 5 volts. Are you with me? Yeah. Of course, you only need 3 pins from it. Or 4. I'm going to need the TX, the RX, TX, RX. You're going to need your VDD, and you're going to need your GND, which is your ground. So if you satisfy these 4 conditions on the microcontroller, your Bluetooth will work. But understand that if you have a Bluetooth device that loses those, and you need to communicate, you need to actually connect to your controller. Let me just say that quickly. Please. Say this is your AC05. Say this is your microcontroller. Your TXD here should go to the RX of the microcontroller. While your RXD will go to the what? TX of the microcontroller. The VSS here must be the VSS here. Are you with me? Then your positive 5 volts. Are you with me? And then this one too will also require what? Voltage. And then you are fine. Now in communication or in serial communication, they do not need to share the same positive voltage, but they must share the same what? Negative voltage. It means that the microcontroller can actually be operating at 10 volts or even at 5 volts, and this one can be operating at 3.5 volts, and that's going to communicate. The only issue you should just know, let me just say that, which is very important, is that transmission will happen based on the magnitude of voltage that it has. So let me explain that. If my microcontroller was operating at say at 5 volts, and the Bluetooth module was operating at 3.5 volts, when it transmits to the microcontroller, it will transmit its voltage at what? 3.5 volts. And that voltage can look low, since the microcontroller itself is operating at what? 5 volts. When the microcontroller is now to transmit to the Bluetooth module, what will it do? It will transmit at what? At 5 volts. That voltage might now seem too high for the what? For the Bluetooth module, since it's only operating at what? 3.5 volts. So it will mean that one, you are going to need a way to step up this, what this one is going to be transmitting to this guy from 3.5 to 5 volts so that he can understand it. And then step down what this microcontroller is transmitting to the receiver here to what? 3.5 volts for you to actually understand it. Does it make sense? Yeah. So to curb all of those happening is why you should operate both at what? At 5 volts. Are you getting me? Yeah. Even though a resistor network was brought in here to drop what the microcontroller was going to be transmitting to this guy, because this man will not receive at 5 volts, will receive at around 3 point something volts. Are you with me? But it's safe to say that both your Bluetooth module and your microcontroller requires what? 5 volts to operate. And like I said, the transmit button here goes to the receive button of this, while the receive button of this goes to the what? To the transmit button of this. Are you with me? When I'm talking, it's your ear that is working. While you are talking, what works with me? My ear. Did you get it now? Eh? Transmit to receive. Transmit to receive here. Eh? So establish 5 volts for this one. So let me run quickly. Before the class gets too long. The LED, the indicator, requires 5 volts to operate at 5 volts. Even though we are going to have a current limiting resistor that limits current and voltage to it. Are you with me? Since we are agreed that across the light emitting diode we should only have what? 2 volts there. So if this man is bringing out 5 volts and at the maximum of 25 milliamp, we can actually use the resistor to actually limit current to it while saving what? 3 volts on the resistor or across the resistor. It makes sense. Yes. You understand that? Okay. So another man, you have a relay. The relay in your system is a 12 volt relay. Let me just quickly say what a relay is. Quickly. If you pick up a relay, you know, I gave you this analogy of you making error. And I mean, you have put water on fire, you want to make garri, and then you put garri in the water, and then all of a sudden, you just realize that I need to turn this garri. You don't dip your hands into that hot water. You go and get maybe a turn stick or something. I mean, that's what they call it in English, to begin to turn the error. So what you are doing is you are using your own very weak power here to control something heavy on the other hand. You get my point now? Since you can't put your hand directly into it. Relay many times always have two sides. You always have the side of the coil, then you always have the side of the contact. Now, so a relay is going to have two coils. So you have something like this. The relay should look something like this. The relay is going to have what we call the wiper. There's going to have one side that is called the normally closed contact. The other side, the normally open contact. Are you with me? Yes. So your wiper is going to look something like this. The normally closed contact. While normally open contact will look like this. So your wiper is like this. The wiper is like, of course, the word wiper. You get wiper if you have, if you have sat in front of a car or any vehicle. You know the wiper always has a rest position.
Yes.
That rest position is the normally closed contact, which means it rests on that side. But when you operate it, what it does is that it leaves its normally closed contact and flips to the normally open contact. Are you with me? That's how the relay 2 works. The moment you energize the coil of this relay, the wiper will move from this normally closed contact and then latch itself to the normally open contact. So whenever you place on this wiper will be on this normally open contact. Whenever you place on this normally open contact will be on this wiper. But the moment you remove voltage, you disengage voltage from the coil of the relay, it loses. Once it loses coil voltage, the wiper returns to the what? Are you with me?
Yes.
To the normally closed contact. So this is what happens. If you are going to use a relay here, and we are saying that the relay you are going to market to go and get is a 12-volt DC relay, that is the coil rating. For the contact, they've told us that the contact can actually stand 10 amps at 240 volts AC. It's actually always written on the body of a relay. It's always written there. Sure, makes sense. It's always written there. Now, of course, we are still going to actually explain relay later in our class, eh? So let's just run with it. So it will mean that my supply should also be able to actually cater for what? 12 volt DC. Are you with me? Yes. And the 220 volt or 240 volt AC that this relay is going to be impressing at the output of our load. So that already is consistent with the AC we want to bring in. We already know we are bringing 5 volts, but we also now know that we are bringing what? 12 volts. So our power supply should be such that can give us what? 12 volts DC, 5 volts DC. Are you with me? Yeah. And then 220 volts what? AC. Sure, makes sense. Yeah. You get the point now. So it is after you have actually gotten all of this understanding that you can then say, oh, I want to design my power supply. If you have not actually correctly calculated and found out what the voltage requirement of every module you'll be bringing into this system is, you cannot say you can't create a power supply. Does it make sense? Yes. So if we've understood that, what should our power supply then look like? Let's answer that question. Are you here? So if this man is if the design is an AC system, it means we don't manufacture AC now. AC comes from mains, from NEPA and the rest. All we just do is create a conduit, to allow the AC onto our board. So the first one we want to bring in will be what? Will be a transformer, isn't it? We'll bring in a 220 volt AC transformer, maybe that step down voltage to 12 volt AC. Are you with me? So we'll bring in a transformer. The transformer steps down that voltage to 12 volts. Are you there? Yes. Then that voltage is sent into a bridge rectifier because we don't need the 12 volt AC. The output of that voltage is then filtered before it is sent into a 7805, our voltage regulator, and the output of that voltage regulator filtered with another an electrolytic capacitor. Yes. So this, of course, will be your 1N4007. 4 of it. So you can go to market and get a bridge rectifier. This will be your 1000 microfarad 25 volts, and this is going to be your 100 microfarad 16 volts capacitor. This is your 1725 voltage regulator. Are you with me? Yes. And then right here, you have your plus 5 volts DC, isn't it? What voltage will you have here? Sulaiman? What voltage will you have at this point? 12 volts what? Thank you very much. You know why? Because here we expect that our bridge rectifier will have converted our AC to what? To DC. But of course we know that if two of those are going to clip in a positive and a negative, and they are made from silicon, and they have to drop 0.6 across themselves, you are going to have a combination of what? 1.2 of that voltage. That voltage is going to be around 10.8. IB? But for the sake of this class, we can say what? We're going to find 12 volt DC there. The 12 volt DC that you're also going to find there, please look up, will also be because the NEPA is supplying you what? 220 volt. If the 220 volt drops on the primary side of the transformer, your secondary voltage of that transformer will also do what? Will also reduce. But I already established that. Does it make sense? Yes. So this is what your power supply circuit diagram would look like, or should look like. I believe that is what should. Whether I believe that's what is there. I believe that's what is there. Oh, one thing we do not actually make provision for a switch. I mean, we should make provision for a switch. I mean,
Yes.
now if the switch is on this side, it means that when we hold the system, the primary side of the transformer is still on. Abi, listen to me. Don't say what we have not said. I'm saying if the switch is here, if you open the switch, of course your system goes off, but your transformer will still, your transformer is still in light. So wouldn't that be better if we place the switch here? Are you with me? And leave this here, so that if you have your source here, of course your source comes in here. AC, well, this implies that it's AC, your life and neutral. When you open this switch, what happens is that you create open circuit and then your transformer is not actually working when you open the switch. Does it make sense? Okay, so that's it. Can I continue? Can I continue? So I can clean the board. So with this now, I've made provision for what? So the relay that requires 12 volts to energize this coil gets its 12 volts from here. Why other circuitries of the system that requires 5 volts will get what? They are 5 volts. And then those sides that requires AC get their AC from where? From the source. Are you with me? Yeah. That is why it's easier. So if you look at this wire, you realize that I've actually joined all those wires together here. So that when I put this into the light socket, are you with me? Or both the voltage, and I put it into either my generator or my NEPA or wherever. Voltage is available. Are you with me? Yeah. At the primary side of the transformer, voltage is also available here. Does it make sense?
Yeah.
I mean, so we don't have to be bringing wire from here and then this one goes to AC and we have bridged them and we join them all together. So you get my point? So that's why I said there's AC on the board. The AC that this man needs, the AC that the system requires to impress on this system is already available on the board. And it will be to me. Abi? Okay, let's fire again. So that's answering for the what? For the power supply. So let's clean quickly. And they're wrong. So I can come to this point and say I've answered for my what? My power supply. I've also answered for the current sensor. Sir?
Yes, sir.
I've answered for the current sensor. Even the microcontroller. Yes. And I've also answered for the LED. Because we know that all we did was just bring in your microcontroller, get in a resistor, and then put it into ground. And then you have that. Microcontroller is going to give you 5 volts. We expect 2 volts across this resistor. I mean this light emitting diode. We know that light emitting diode would operate from between 1 to 40 milliamp. The microcontroller will operate from 1 to 25 milliamp maximum. But we don't want this light emitting diode to get all the 25 milliamp that the microcontroller has to give. So we can say, okay, maybe 1 10 milliamp to flow, 1 6 milliamp to flow, 1 5 milliamp to flow, or even 2 milliamp to flow. The choice is yours. But we know that if you use 10 milliamp to flow, that's always very easy for me to calculate with. So we just use Ohm's law and say R is going to be what? V is by what? I, and our V is going to be what? 5 minus the 2 that we want across here. Or by what? 10 times 10 minus 3. And I told you your R is going to be what? 300 ohms. But of course, I don't use 300 ohms. So it means I don't allow 10 milliamps to flow. I use between 330 ohms to what? 390 ohms. So it means less than 10 amps is what is flowing in this place. I said that because I don't want you to ask you to calculate again and then begin to give me some value that make me look like like a boss babe. Can we continue? Yeah. So we have answered for the light emitting diode too. We have also answered for the Bluetooth module. Yes. Abi? I've told you quickly what it is. But there's something I would have loved to say to you guys on it, but let's leave that. Then I think I've answered for the relay now. Told you.
Answer for the relay.
Let me just tell you quickly how the answers for the relay. Eh?
The answer for the relay just now.
You didn't see how you answered for the relay.
Okay.
You didn't see it. You didn't see it. Please look up. Now that you guys have agreed that I did, I'm not going to explain. So but look up. Now the truth is, the microcontroller can actually not give you 12 volts to power your relay. The relay requires 12 volts to come on. Microcontroller does not have 12 volts, that's just 5 volts. So what you do is that you bring in a transistor as a switch. Let me explain how the transistor and switch is. From one of the outputs of the microcontroller, you decide which of the pins you want to use. And I've said before you left yesterday that the microcontroller pin is defined by a port and an address. So if I'm on port A, bit 1, I can also be on port B, bit 2, I can also be on port C, wherever bit. Just know that, of course, your port B will have a full 8 pin, including your port C, your port D, except for your port A and your port E on the smaller ICs and then on the 40 pin ICs. Can I continue? So you are going to have a resistor that goes to the base of the transistor. Have we treated transistor in our class?
Transistor.
Yes.
No, sir.
No, sir. Have we? Then what have we been doing all this while? We have been playing, have we? So this is what happens. Let's look up. Transistors usually has transistor usually has 3 contacts. Are you with me? The base, the collector, and the emitter. Just stay put that when you bias the base of this transistor with 0.7 volt of voltage, are you with me? The collector and the emitter becomes like an ordinary wire. Looks like an ordinary wire. Are you with me? They connect so that wherever is on the collector, it becomes impressed on what? On the emitter. Are you with me? And when you remove that base voltage, it's isolated. Then now becomes a very high resistance between them, so that wherever is here will not be here. Now, if I wanted to use as a switch, are you with me? Don't forget that your relay will require positive and negative. Let me explain what I mean by positive and negative. Please, just forget this. If you have a voltage source, DC voltage source, so which means you have positive, you have what? Negative. If I have a bulb too, that requires positive and negative. If I want this bulb to come on, are you with me? I will give negative to negative, isn't it? And I will give positive to what? Positive. If I need to bring in some level of control, what I can do is to bring in a switch, so that when I close the switch, the bulb comes on. When I open the switch, the bulb goes up. That is exactly what I'm going to do with this transistor and the relay. But don't forget, the switch is only on one side. This condition for one side has been satisfied. I'm only injecting one of the lines. I impress, I eject. I impress, I eject. I impress, I eject. Does it make sense? You get my point now? So that's what I'm going to do with this. Now, your relay, of course, your relay should look just that place. Okay? Plus 12 volts, and then I'm going to bring in the relay this way. So this is going to be the coil of your relay. The positive side of the relay, and then the other coil. Are you with me? So you bring in your coil on the relay like this. But look at it. I've given the positive side of the relay is 12 volts. Are you with me? So what is the other side looking for? What's he expecting? What's the other side of the relay looking for? 12 volts what?
DC.
Positive or negative?
Negative.
Negative. Because I've already given it what? Positive 12 volts on this side. Isn't it? Like what I did here. Assume that this is the positive. And I want to put the switch on the negative. Are you following me?
Yeah.
Just need to just run through it. Are you with me?
Yeah.
So this is the positive. It has gotten the positive. For the negative, I now connected the negative to the collector of the transistor. And now to the emitter of the transistor to what? To the ground that it's looking for. So what it means is that when I bias the base of this transistor acts like an ordinary wire. Are you with me? And then closes up so that the negative side of this relay gets what? Negative on the collector. And then the relay will switch. Are you with me? So that the relay then switch from the normally closed contact and switch to the what? To the normally open contact. This is the wiper. Okay. So, so earlier I was I was trying to explain what actually was happening with this relay, or how the relay was connected. So let me quickly go straight, and then we can actually bring this class to a whole. Okay, so I said that because, please look up. Now look at this. Look at this. I said if this was a source, this was my DC source, and this was a bulb, I can actually have a switch here. Are you with me? That I disengage and engage, or I switch. I turn on and turn off to apply voltage to this bulb and have this bulb light. Are you with me? So I can always do that. Now I can actually I can have the switch either on this side of the relay, on the negative side of the relay, or I can have it on the what? On the positive side of the relay. The choice is mine. So what I actually intend to do here with this transistor and switch is this. It's as good as having the positive side connected, and I came here and I brought in a transistor. Are you with me? Yes, so this is the collector of the transistor. Now. Okay, no. Now, the role that this switch will play, let me do that out. I always talk about that one. The role that this switch is playing, if you look at it closely, what this switch is actually doing is, why one of the lines is connected, why one of the voltage range condition has been satisfied. What I'm doing here is when I close this switch, this bulb comes on. When I open this switch, are you with me? The bulb goes on. But don't forget, this is a mechanical switch. It will mean that I have to be coming to turn it on and turn it off, turn it on and turn it off myself. Liking this operation to what I want to do here. If this was the relay, are you with me? Yes, assume this was the relay. For the relay to work, the relay we did is positive line and the wire what? Is negative relay. Now, come to think of it, that if I am taking the positive side of the relay to the positive 12 volts that came from my power supply, for this relay to be energized, what the relay is waiting for will then be what? His negative side. What I now did was I now kept the negative on the emitter of this transistor. Are you following me? Yeah. I kept the negative that the relay is looking for on the what? Emitter of the transistor. And I took the collector of that transistor to the negative side of the relay. It's such that whenever I bias the base of this transistor and the collector and the emitter loses the high resistance in between them or in between it, and it closes up like a wire or like a wire string across it. What happens is that the negative side of the relay through the collector of this transistor will connect to the emitter of this transistor and then to ground. Are you with me?
Yes.
And the moment I take off my bias voltage, what happens is that resistance is returned, and then the relay loses what? The negative it's looking for, and then loses its coil voltage. Are you following me? Yes. So while I would have been mechanically doing it here, I'm now electronically doing it here. Are you with me? It's why you call the relay an electromagnetic switch. Are you following me?
Yes,
are you with me?
Yes.
So, of course, all I needed to do is to control its coil voltage, because I know that once the coil voltage is connected, what will happen is that this wire will move from the normally closed contact and lash to the what? To the normally open contact. Are you following me? Yes. So that's exactly what, how it will have been connected. But let me now go further and now impress it even further. Let me now show you what I will do. Now, since my load, please look up.
Yes, sir.
Please look up. Don't write it. Since my bulb, don't forget, look at that outlet. We have something like this. 13 amp outlet. Are you with me?
Yes, sir.
I think this is too big. It doesn't look like it at all. We have something like this. So you have this, and we have this, and then we have that.
Yes, sir.
So assume that this is your life, Let me just put it here. As this is our life, this is the neutral, and then what do you call it? Earth, have you? Have you? That's what they call it. Now, if I want voltage to press here, don't forget that the voltage that is to be repressed here too must be the voltage that is coming, that is feeding the primary coil of the transformer. It's still from our source. So assume we have a source here. Are you with me? This is the source. So call this your life. Are you with me? Call this your neutral. What I can actually do is to connect the life to this place. So the life is connected. So what is this socket waiting for to come on?
The neutral.
It's looking for the neutral. I will not take that neutral. Please look at what I'm going to do. I will then take the neutral and connect the neutral. I can connect it to the wiper. I will not take the neutral of the socket. I'll use another pen, color here. I will not take this neutral here. I will not connect that neutral to the what? To the normally open contact.
Alright.
So, why the microcontroller does not bias, or why I do not have the microcontroller to bias the base of this transistor? The wiper that is carrying the neutral is latched on the normally closed contact. And that normally closed contact is not connected to anything. So the voltage is just there. Are you with me?
Yes.
Now, the moment the base of the transistor is biased, don't forget that this socket already has life from the source. What is waiting for is the neutral.
Yes.
I've now placed the neutral on the wiper. The wiper will just come and lash on normally open contact. When it lashes on normally contact, what happens? It connects what? The neutral it already has through the wiper, through the normally open contact, to the what? To the neutral of the socket, and then light is impressed on that socket. That is how voltage gets to the socket. What I have done is I have taken advantage, two advantages here. The microcontroller cannot actually supply 12 volts, neither can it connect to an AC appliance or an AC load. So I brought in transistor as a switch to help me impress negative to the what? To the coil of the relay. And I use the contact of the relay to switch what? AC. Again, almost repeating the same analogy I gave about making garri and getting toner instead of what? Using your hand. The same analogy about using broom or holding broom in time to sweep. But of course, you are actually the one who is affecting the, who is actually putting the effect. But of course, you are not the one who is doing the sweeping.
In this case, this transistor is acting
As a switch?
a switch, and is it acting as a current amplifier?
No. Acting as a switch. I've not taught you how to use transistor as a current amplifier.
Okay.
So I did not expect you to ask that question.
Okay.
Because I've not taught anything of such. The only time we were to mention it was when we were talking power supplies. I only said transistor as a switch. Never mentioned that. I don't know where you got that from here. Of course, we said that while we were discussing regulated power supply using Zener diode. And I showed what transistor could have been used for as a switch. Then, even though I actually did not actually expatiate on it. Okay? So, but here is as a current amplifier then. But here it's actually being used as a switch. It's just an overview to actually just satisfy the guy who needs to pick up this project and go. Are you with me? Yes. But this is how the relay with a transistor is used to impress voltage here. But don't forget the condition for why this relay is going to either, why this microcontroller will actually turn this relay on or off is this. Why the current sensor has a load connected on it, which means every time you run the system, when the system does force it to go and check, what amount of current is being drawn? Lesser than 10 amps. Okay? What does it do? This place comes on. Are you with me?
Yes,
the output of that of the microcontroller is on, biases the base of the transistor. The transistor does what? Connects ground or negative to the coil of the relay, and then the relay switches, and then you have voltage here. So whatever appliance you have connected here, like the iron, like all of the other things we've tested with, the soldering iron and the rest, and with the pressure iron and soldering iron, you find the load here, and then current is being sensed. Now, as you load this output, As you load this output, so as you continue to load this output, what happens is that the current is then being what? Don't forget. What am I going to say this? The current sensor will actually be across this point or one of these points. Therefore. Don't forget. Don't forget I said the current sensor has two parts. Are you with me?
Yes, sir.
So the current sensor is actually going to be here. So that one part of the current sensor is here. The AC side. Are you with me? Why the DC side that already has VDD, VSS, and then the out goes to the what? To the ADC input of the what? Microcontroller. Are you with me?
Yes, sir.
Are you getting it? So across that in between the load that connects here is where your what? Your current sensor is. What's that current sensor again?
This
ACS
is
712. Are you following me?
yes, sir.
Please look up. Does it make sense?
Yes, sir.
Does it make sense? So that's actually what happens here. Now, as you apply load here, the current sensor is sensing it. As it's sensing it, analog output is being fed into the analog inputs of the microcontroller, and then it's measuring it. It's incrementing. It's measuring it. In the code, we had already written that the moment the current hits 9 amps AC, what should happen is that the microcontroller automatically sends an off
To that point.
to the point of this, to the base of this transistor through this resistor, and then the moment it puts it off, what happens is that the collector and emitter is disengaged. Are you with me?
Yes, sir.
The relay coil does not get negative anymore.
Yes, sir.
And then the wiper returns to the what? Normally close contact. And then what happens? The current sensor does not sense anything again. And once this line is not completed, or is not complete, what happens is that wherever you connect it goes up. And when it goes up, the current sensor begins to read 0. Of course it's off. Now, it does not mean that the system is off. No. It's not off. The truth really is, if you continue to apply more load to it, the relay is going to go off. Because the contact of that relay can only stand 10 amps. Are you with me?
Yes.
So what we have actually been able to do quickly, what we've been able to do quickly is to protect this relay from going up. Because if you actually have applied a load that draws or that requires 6 for more than 10 amps, the contact of that relay will not be able to stand it. And then it will go up. So before the relay goes up, what we have done is to disengage the system ourselves. That is the foolproof that we incorporated into the system. But while it's carrying out this operation, it actually writes on the screen, which of course will be on the Android application. And what is it going to write for us? And what is it going to write to us? Overload. So we know we have actually overloaded the system. We can then remove the load, return a lesser load, and then turn it on and start the process again. Are you following me? So if you ask what the eventual circuit diagram will look like, of course I might not be able to draw the power supply. I haven't drawn it before. Please hold on. What we then will have is something that looks those. So hold on. I said that the microcontroller we are using is what? Is a PIC. Is a PIC 16F876C. Are you with me?
Yes, sir.
Now, from, of course, I'm not supposed to also say this from my, off head, but let me just give you the details. In that this microcontroller we request for 1 VDD, 1 master clear reset, 2 VSS, and so 1, 2, 3, 4, 5, 6 is off from the 28 pin. So when you take 6, you are left with what? 22 input output pins. Among the 22 output pins, if you go by what we had earlier discussed, to determine how many ports will this controller likely have, we can begin. Of course, we know it's going to have port A, isn't it?
Yes.
We know it's likely going to have port B. if we give 8 to port B, 8 here will give us what? 8, 9, 10, 11, 12, this is 4, 14. So we can actually have port C. If you give 8 to port C and you take 8 from here, what do you have left? 6. Apparently, it means about port A, we have the what? 6. Again, it's in tandem with what I already discussed in the previous class. I do not have to look at the data sheet to come up with this. The facts are that port B will have a complete port, port C, even a port D, but the port E will not have a complete port, and so will port A not also have 8 pins. Does that make sense? Are you following it? Okay. So I expect that this controller is going to have port A, port B, and then port C. Let me get the data sheet. Actually be able to actually give you some details. I will not dwell long on it. I will not dwell long on it. I will just I'll find an image of it. Okay. Okay, please look on. Now, from the data sheet, I can submit to you. How many input output did you say we are going to have? 22 input output. So I can submit to you, please look on.
Yes.
That your master clear reset pin is going to be your pin 1. Your VSS is going to be your pin 8 and 19. Yeah? You with me?
Yes, sir.
Your 19. Your oscillator pin. This is specific for this microcontroller.
Yes, sir.
Will be 9 and 10. In 9 and 10. While your VDD would be your pin 20. Does that make sense?
Yes, sir.
And please look up. It means if it has port A, port B, port C.
Yes, sir.
Are you with me? Please look up. You are then going to have RAO, RA1, RA2, RA3, RA4, RA5. Isn't it?
Yes.
Numbering, pin numbering will be 2, 3, 4, 5, 6, and then 7. You are going to have RB0, RB1, RB2, RB3, RB4, RB5, RB6, and RB7. You following?
Yes, sir.
From RB7, it will be 28, 27, 26, 25, 24, 23, 22, 24. You do not actually have to write this. You just get the data sheet is there. Are you with me?
Yes, sir.
Then you have the RCO, RC1, RC2, RC3, 4, RC5, RC6, and RC7. Your RCO begins at pin 11, 12, 13, and 14. Then 15, 16, 17, and 18. That's just how you add it. But don't forget one other thing I actually mentioned in this class. Please go. Is that not all the pins, like I said, not all the pins. All the pins will serve input-output functions. But some of those pins also still have other functions that they serve. Like we discussed on the 16 I mean?
Yes.
Now, let me give you for this. Are you there?
Yes, sir.
I mentioned that your current sensor, which is your ACS 712, communicates using what? ADC.
ADC.
On this microcontroller, the only port on which you can do or carry out ADC are on your port A.
All of these.
Yeah. Again, when we get to ADC, we'll actually discuss that. But just understand that you could not have connected this current sensor to any other part of the microcontroller or any other port on the microcontroller except for what? Port A. Because that is the only port that is interfaced to carry out what? Analog to digital conversion along with being what? Input output or pin operation. Does it make sense?
Yes.
Does it make sense?
Yes.
Please. Look up again. Look up. If you need to connect your Bluetooth module, which is your AC05, I've told you, hello, please look up,
Yes, sir.
that this Bluetooth module will require VDD, VSS. It has a TXD pin and an RXD pin. And I told you that its own TXD will go to the what? To the RX of the microcontroller. Why is RXD pin will go to the what? To the TXD of the microcontroller. The port on which this can happen will be on your port C.
All of these, you can use any of them.
Not on port C.
Okay.
On this particular microcontroller, it's going to be your port C6 and your port 67. So this is your RB7, RC7, and this is your RC6. Are you following me? They carry out input-output function,
And the fire will be.
but they also carry out other function. Now, but please look up and listen to this word. This is key in discussing USAT or UART. We'll be using this particular pin because this is the only pin that is interfaced with the internal hardware transmit receive module of this microcontroller. It does not mean to say that we cannot create transmit receive operation on any other pin. We can, because that's what would then be called the software UART. What do I call it?
You are.
Software.
You are.
But this is the dedicated pin or the dedicated port for carrying out communication transmit and receive operation. Are you with me?
Yes.
But the controller also offers us the opportunity of creating our own software transmit receive operation on any other pin or on any other port on the controller. I just needed to see that here.
Yes.
Of course, we will have a better understanding of it as we proceed in our training. Are you with me? Okay. Something else to note. So we handled for the current sensor, we handled for the Bluetooth module. Of course, the LED could have been on any pin or on any port, isn't it?
Yes, sir.
So I'm not specifying that you can actually pick a pin at random, unless I need to say it to be in tandem with what's already been designed. What other thing did you say the system was going to have?
He said the system was going to have a relay.
A relay. So the relay, of course, will also be on another pin. Are you with me?
Yes.
So I'm going to have the relay, of course. Just call it the relay circuitry. Because don't forget, there's of course a transistor. Now there's something I forgot to say to you. So I don't know why that escaped my mind. Because the relay actually has coil. Are you with me?
Yes, sir.
There, I mean, look at what I drew before. I said transistor. You following?
Yes,
I
sir.
said this is the relay. I said it has gotten what? Plus 12 volts. Have you?
Yes, sir.
I said it has the wiper, the normally close contact, and the normally open contact. So this is the wiper. We usually have a diode in a reverse bias mode across the coil of the relay. Because it's a coil, as much as you can energize it, when you withdraw your 12 volts, it can actually return voltage back to the board, to your system. Are you with me? So to block that reverse movement or that back EMF is why you always have a diode in reverse bias module. And don't forget, we had already mentioned that one of the properties that the diode has is what? Avalanche voltage, isn't it? And if we had used a 1N4007 here, his avalanche voltage is what?
The avalanche voltage
It's 100 volts. 100 volts. The voltage it can block. Maximum 1N4007. Have you forgotten? Why it can allow a maximum of just 1 amp across it? Can you recall?
Yes, sir.
Can you recall?
Yes, sir.
You don't look like you recall though. Now this is application. Are you with me? So this, of course, should be how it should have been drawn. I omitted this one, this diode. Are you with me? So that's why I said it's going to be relay circuitries. Are you with me? So you have the relay circuitries on one pin on a port on the controller. You have the LED on one pin on a port on the controller. You have 2 pins for your transmit, and then you have 1 for your ACS. So in the how many pins did you say we have left? Input output pin 22. So in the 22, we had only used 1, 2, 3, 4, 5. So we had only used 5 pins. All we left.
We left with
17 input output pin are used. But really, in the initial design, I had LCD connected on the port B. Between the RB1 to the RB7, I had an LCD there. That was the idea. Before we decided to actually bring in some changes to the design, such that it does not look like what's already available, obtainable somewhere. Are you with me?
Yes, sir.
Are you with me?
Yes, sir.
So, but of course, if you take that out, if you have added this would have been 6 pins. Are you with me? So you could have taken from your 7, you have taken 6 pins, and then you have had 11 pins left. But if we take this out, it means that we have what? 17 input output pins. The question therefore will now be, are there no smaller microcontrollers with lesser pins? Are you with me? That could have actually just carried this process out without actually, because 17 input output pin. Of course they are. Are you with me? They are. What the next good question will now be is, maybe those ones will lack the amount or number of program memory that this project will have required. Does it make sense?
Yes.
Does it make sense?
Yes, sir.
Because if you look at it, your PIC 16F, either 628A or 648, can actually carry out this UART function because it has it, but does not have ADC.
We need an ADC.
And you're going to need that ADC. I believe that your 12F675 should actually have ADC, not comparator. If it has ADC, and you can actually get maximum of 6 input output pin from it, I don't think it has UART. Unless you want to actually program into it a software UART. And could not have had enough memory to have held this program.
That's what we wait for this.
Are you following it?
Yes.
Does it make sense?
Yes.
So, in a nutshell, this is what, or an explanation for what you have running in that box today. So, if you're writing something, and then we can just do a very quick 2-3 minute physical examination of the project again, and then we can call it a day. Hope you learned something.
Yes, sir.
Have a question?
Yes, sir.
Thank you very much.
Thank you very much.